Welcome to Demystifying Math. In this lesson, we're going to be graphing a function that has an asymptote. This is part 3 in a video series on graphing functions with asymptotes. In this video, we're going to be graphing f of x equals x squared minus 3x over x squared plus 6x plus 9. The first thing I'm going to do is go ahead and factor the numerator and the denominator. So with the numerator, we see that it has a common factor of x. So we have x times x minus 3. And the denominator is a perfect square, so we factored it as x plus 3 all squared. In its factored form, it's easy to see what the domain of the function is. This function is going to be undefined at negative 3. So what we want to do is decide whether or not there is an asymptote at x equals negative 3. So we're going to look to see what happens to the function as x approaches negative 3. So I'm going to plot a few points near negative 3. I have negative 2.7. I got out 171. At negative 2.8, I got 406. And at negative 2.9, I got 1711, which shows me that the numbers are increasing rapidly for our output values. So that means that our function is heading toward infinity. And that's just on the right side of negative 3. Let's go on the other side of negative 3 and see what happens. So I'm plotting in negative 3.3, negative 3.2, and negative 3.1. And again, the numbers are rapidly moving up toward infinity. So this limit is also going to infinity. So we would say that the limit as x approaches negative 3 is equal to infinity, which means that our graph is unbounded. And if it's unbounded, that means that there is a vertical asymptote at x equals negative 3. Okay, so now what we're going to do is look for a horizontal asymptote. And we're going to do that algebraically. What we're going to do is go through and divide each and every term by x squared. Always use the variable to the highest degree when you do this division. So we're going to simplify now. So x squared over x squared is 1. We're simplifying the 3x over x squared to 3 over x and doing the same thing in the denominator. Now what we want to do is take the limit as x goes to infinity. Well, if you have 3 over an extremely large number, that means it's going to be extremely close to 0 when you divide it. So the 3 over x is going to head towards 0, the 6 over x is going to head towards 0, and the 9 over x squared is going to head towards 0. So the only thing that we're left with is 1 over 1. So our limit is 1, which means that we have a horizontal asymptote at y equals 1. Once in a while, a graph will cross its horizontal asymptote. We should check and make sure to see whether it does or not, because that would be an important point for us to graph. So we're going to take our function and set it equal to 1 and see if we can get out any solutions for x. So I'm going to multiply both sides of the equation by x squared plus 6x plus 9. So on the left side I'm left with x squared minus 3x, and on the other side I have x squared plus 6x plus 9. You should see quickly that the x squareds are canceling out. Then we're going to bring our 6x over to the other side with a negative 3 and divide by negative 9. So I do get a solution here. At x equal negative 1, the output is 1. So I have the ordered pair negative 1, 1 on my graph. You can verify that by plugging in the negative 1 if you need to. So in this case, the graph crosses the horizontal asymptote at negative 1, 1. Okay, now that we have the asymptotes, what we want to do is find the intervals on which the graph is increasing or decreasing. And we're going to do that by taking the first derivative. Since this is a quotient, we're going to use our quotient rule. U is going to be our numerator and V is our denominator. Notice I also rewrote them in their factored form because sometimes it's a little bit easier to work with the factored forms. The derivative of the numerator is 2x minus 3, and the derivative of the denominator is 2x plus 6. We're going to plug that into our quotient rule formula. So with our quotient rule, we have v times u prime minus u times v prime all over v squared. And notice I wrote everything in factored form. So now what I'm going to do is factor out the common x plus 3 terms. So this has a common factor here of x plus 3, and this one has an x plus 3. So when we divide out the first term, we're left with 2x minus 3 and another x plus 3 factor. Here we're going to be left with the 2x and the x minus 3. Now this x minus 3 is going to cancel with one of the ones in the denominator. Then I went ahead and FOILed out these first two factors here. So I have 2x squared plus 3x minus 9. And I also distributed the negative 2x. So that gave me negative 2x squared plus 6x. And I'm going to go through and combine like terms. So what you should notice is that the 2x squareds canceled each other. So we were left with the 3x plus 6x, which is 9x, minus 9. And then I factored out the 9. Now it's in factored form. It's really easy to see where your critical points are. Remember, your critical points are going to be wherever your numerator is equal to 0 or where your denominator is equal to 0. So we have negative 3 and 1 as our critical points. Alright, now that we have our critical points, we're going to go ahead and draw our number line and test points between and beyond our critical points. So I chose a point below negative 3. I chose negative 4. And I plugged it in and got out a positive 45. Since I have a positive number, I know my graph is increasing on the interval from negative infinity to negative 3. Between negative 3 and 1, I chose 0. I got out negative 1/3, and that is a negative number, so I know it's decreasing on the interval from negative 3 to 1. Above 1, I chose to put in 2, and I got out 9 over 125. It's a positive number, so again, the graph is increasing from 1 to positive infinity. Remember that we had a vertical asymptote at negative 3, so that can't be a turning point. But we don't have an asymptote at 1, so it could be a turning point. And it is a turning point because the graph moves from decreasing to increasing. It's actually going to be a minimum point because the graph goes from decreasing to increasing. So what we want to do is plug 1 into our function. And in this case, I got out negative 1/8. So that means that the ordered pair 1 and negative 1/8 is a minimum point. We don't know yet whether it's absolute or relative, so we're just going to call it relative minimum point. Okay, so next we want to look at the concavity of the graph, and we're going to do this by taking the second derivative. So looking at our first derivative, our numerator is 9x minus 9, and our denominator is x plus 3 all cubed. And we took the derivative of both of those. Then we're going to plug into our quotient rule. Our quotient rule says that you're going to take vu prime minus uv prime and divide it by v squared. Now again, I'm using the factored forms because I can see obviously that there's an x plus 3 in common to everything. Actually, there's an x plus 3 all squared in common to everything, as well as a 9. So I'm going to factor all that out. So in the brackets, I'm left with x plus 3 minus 3 times x minus 1. And now my x plus 3 squared over my x plus 3 to the 6th are going to cancel 2 of those, so I have 4 of them in the denominator. I still have the 9 left in the numerator. Then all I did was distribute the negative 3 here, so I had negative 3x plus 3, and then combine like terms. So I have x minus 3x, which gives me the negative 2x, and the 3 plus 3, which gives me the 6. Now the 6 and the 2 also have a common factor of 2, so I factored that out. 9 times 2 gave me 18, and I'm left with 3 minus x. Now since I had a negative variable here, I went ahead and factored out the negative. So I have negative out front and x minus 3 in the parentheses here. So this is going to be my second derivative. Now we have critical points at negative 3 and 3. Remember, your critical points are wherever your numerator is equal to 0 or where your denominator is equal to 0. Now that we have our critical points, we're going to set up our number line. So we want to plug in a point below negative 3, so I chose negative 4. I got out a positive 126. Positive numbers tell me that the graph is concave up. So it'll be concave up from negative infinity to negative 3. I plugged in a 0, which is between negative 3 and 3, and I got out positive 2/3, so it's still concave up there. But remember, in between, we have a asymptote. So anything could happen to the graph when there's an asymptote. We could change directions or not change concavity. Alright, so let's go beyond 3, and I plugged in 4. I got out a negative there as well. So that's going to be, the negative there instead, so it's going to be concave down. Now remember that we don't have a an asymptote at 3. So 3 would be a point of inflection because that's where it's changing its concavity. So what we want to do is find the ordered pair. So we're going to plug 3 into our original function, and I got out 0. So 3, 0 is an inflection point. The inflection points, the maximum minimum points, any points where the graph touches an asymptote are important points for you to graph. The other points that we're going to do are just random points. I did a few on each side of where the turning points are in the asymptotes. But choose enough of them so that you know where the branches of the graph are. So -5 I got out 10, -4 I got 28, -2 I got 10, 0 is 0, and then I plugged in 4 and 5 so you can estimate those. Now what you want to do is go ahead and draw your graph. You're going to start off by drawing your vertical and horizontal asymptotes. Use a dotted line so it shows that it's not actually part of your graph. Then you're going to plot some points. You're going to plot your minimum point that you found at 1 and -1/8. You're going to plot your point of inflection at 3, 0. You're going to plot the point -1, 1 where the graph touches the horizontal asymptote, and the additional points that we found above. To the left of x equals -3, you're going to draw the curve that is concave up and increasing and goes to the points that you plotted. Also keep in mind that you have a horizontal asymptote, so it's going to head toward y equals 1 on the left side. You're going to draw the curve between x equals -3 and +1 that's decreasing in concave up. Between 1 and 3, it's increasing in concave up. And beyond x equals 3, it's increasing towards y equals 1 and concave down. So go ahead and draw your graph, pause the video if you need to, and come back and check your work. On the next slide, I have the graph drawn. Okay, so you should have a graph that looks similar to this one. I have my vertical asymptote at -3, my horizontal asymptote at 1. I have the point at -1, 1 crossing the horizontal asymptote. I have my point of inflection at 3, 0. You can see it changing its concavity there. At 1, -1, I have a turning point, and this ended up being the actually not just a relative minimum point, but an absolute minimum point. It is the lowest point on our graph, and that's because of the horizontal asymptote holding the graph above there on the left side. Alright, and then on the left side you have it increasing and concave up. So check your work, make sure you did it right, and thank you for tuning in.